This is a normal fault. You can see the fault plane extending up from maybe about 50 meters or so, extending down into, so that's the footwall that we're looking at there, extending down into the hanging wall, and that's an active fault, so that generated an earthquake. And the particular earthquake that fault generated was the one I want to start with, because I want to take one normal faulting earthquake and, if you like, unpack it. Talk about what we learned from it. A particular earthquake happened in 1981. And in 1981, there was, in the late 70s, a kind of integrated group of geologists and seismologists that got together such that when there was an earthquake in a part of the world, they would go in with this multidisciplinary team armed with lots of seismographs to kind of unpack them. There was an earthquake in Algeria in 1978. There was an earthquake in Greece in 1978, an earthquake in Algeria in 1980, one in Rome, and then this one in Greece in 1981. So it's one of these examples where lots of different groups from France, from Germany, from Britain all came together. And so it's a very well-studied earthquake. And I think it just gives us an interesting insight into how faults work. So one of the things that noticed here is that this church, it's in Greece, this church is sitting in the sea, probably not where it was built. And so what's happened there is, as a result of the earthquake, we've had subsidence. So this has been sitting in the hanging wall of a fault, and you can see the topography in the background. You can see it's escarpments, and that's the main fault line. So the fault itself, so where we are, Athens is across here. This is Corinth Canal. We're a little bit north of this, a little bit headland that juts out. And this is referred to as the Alkenides Gulf. These are the Alkenides Islands. And there was 3 earthquakes, the 24th and 25th of February, 1 and 2, and then one later in early March on the other side. And they produced ground breakage and ground rupture along this part of this headland, this Perahora Peninsula. A few tens of fatalities. It wasn't especially damaging. It didn't hit a big city, but producing nice ground breaks. Ground breaks up to about a meter or so. So there where you can see that surface would have been connected to that one, ripped open, and you've got your footwall getting pushed up by a meter and a hanging wall dropping down. One of the other things that's interesting, because it's a headland, it allows the geologists to go around and work out if areas had gone up or gone down relative to sea level. So sea level is a really nice datum. So this is where the earthquake was. That picture was along this section here. This is the ground break. It's a bit blurred, but you don't need to really see the details. The key thing is there's ground breakage here, the main fault trace, and then ground breakage all the way to the coastline. And one of the things is going around that coastline, you can see that some parts are uplifting. And they're very clear that they're uplifting because they leave a record of that uplift. So, for example, one here, what we see is a limestone block that's it's been undercut at its lower part. That undercut is where the tidal line was, and it's been shifted up so that it's now above that tidal line. And that's really the characteristic we're going to see. So it occurs just in this little patch here. And then if you go across to this area here, you see that the rock there has got a series of layers on it. They're like tide marks that the sea level had left behind, and that area is now being kind of coming out progressively out of the sea. If you come around to this little headland here, 3 and 4, well, 4 is this beautiful, what's called the mushroom rock. Again, undercut, that's an area that's getting pushed up. And in number 3, you'll see 3 of our PGG students. That's Tim, I think, jumping off there, trying to get a better look at the notches on the bottom left that he flies past before crashing into the water. Because again, what we see there is a series of shorelines. So the geology of parts of these coasts is uplifting. So these areas are areas of uplift. But there's also evidence for subsidence. Again, the text is a bit blurred here, but this is a place called Strava. Let me just go back to show you where we're going to go. We're going to go up to here. This is a place called Strava. And what you see is that there's been the area of kind of low-lying rock has actually gone down. So we're submerging areas. This is areas that would have been up at the beach. Has gone down. So we're dropping it. And jetties that were, so human cultural remains that were tied to sea level have also changed position. So you can see the position where the old jetty, for example, is actually now, because that's dropped down, it's no longer able to function as a jetty, so they've had to build a new one, and they built it higher up in order for people to get off the fishing boats. And so what they did was various teams have gone around this headland, looked at the geological features, looked at the cultural features, and also talked to people, said, well, how much has it been? And so they've argued that it's been, a certain amount of displacement because they were obviously witness to the earthquake. So what's the story? Well, the story is that here's our fault break here. And what we see is that if we track the fault break down, in this area here is Strava, and that was the area where we saw the submerged area. This coastline has been submergent. So during the earthquake, it went down because it sits in the hanging wall. But the break then goes offshore here, and the bit where it goes offshore, the coastline inland of that, inboard, has been uplifted, so you get notches, etc. You also get notches developed down in this area, where again the fault's coming across, and so it's almost more into its footwall. But you also get uplift over here, and that's probably telling you, or that seems to be telling you, that there's another fault that's important that lies offshore that was lifting that coastline on top. Now, this area happens to be quite controversial in terms of some of those measurements, but certainly geologically, that area is rising up. So we must have, it sits in the hanging wall of this main fault, so it should be going down on that fault. But the very fact that it's emerging is telling you that this offshore fault must be active as well in recent times to kind of keep it shunted up. So what you can see then is a number of fault strands, this being the active one, but others obviously important in the dynamics of that local area. Mentioned the fault. This is the Pisa fault. It's located just in here. The earthquake happened about 10 kilometers down. That's kind of typical, isn't it? We've heard seismogenic zone, the base of that's where the earthquakes tend to nucleate. That tends to be between 10, 12 kilometers down. The distance from the ground break to the Alkanides Islands, is there a scale on here? That's about 10 kilometers as well. And so the actual fault itself, the fault plane, is about 48 to 50 degrees dipping surface. So basically what it means is you can project this fault down at, say, 45 degrees, let's say, and it will go 10 kilometers. So by the time it gets 10 kilometers out, it's 10 kilometers down. In other words, the earthquake nucleated right underneath the Alkanides Islands and then ruptured up to the surface along what we think is a broadly planar structure. It's James Jackson, who was leading a lot of these at Cambridge now, a lot of the groups there, and has worked a lot on this. And this is his, in his paper, his diagram. This is where the Pisa fault would be. It's just showing you that big fault plane. And basically it seems to go down at a broadly, as far as we can tell, planar attitude, all the way down to the location of that second earthquake we think the 25th of February, happened in the middle of the night. So everything to the right in the hanging wall drops down, including the coastal zones there, and everything on the footwall rises up. Now, one of the things that James Jackson's kind of looked at was this notion of what are the depths of faults. And these tables, or these histograms, come from compilations of focal mechanism, earthquake mechanisms, where you can determine the attitude of the nodal planes, of the fault depths. So what it shows really is that by far and large, most of the fault depths that occur in normal faulting earthquakes, just normal faulting ones here, are moderately dipping. They're between 40 and 50 degrees. Very few, and in terms of this with surface breaks, if you look down this one, so this would be, for example, the 1981 Corinth earthquakes, very few active earthquake-generating faults seem to have fault planes of less than 30 or less or above 70. So they're moderately dipping. So that would argue that you don't get active low-angle normal faults, and you don't really get active very high-angle faults. Both of those are hard to drive, hard to generate. So instead, what we're looking at is most normal faults, that, and this is what comes out of the Corinth example, being broadly planar structures at a moderate angle. That seems to be the characteristic of normal faulting. What do we learn from elsewhere? Well, this is a nice example. This is Borah Peak. This is in Idaho, an earthquake in 1983. A big earthquake, over a magnitude 7, I think. And the interesting thing about that one was that they had done a surveying line just prior to the earthquake. And so when the earthquake came, they resurveyed the same line, and they found displacement. And you can see the dots on that top graph show what happens to their elevation change, and it's elevation change in millimeters. So that's about 1.5 meters, or 1.2 meters, in terms of that vertical one there. So what you see then is you'll see that this all connects up. So this is the earthquake, occurs at a depth of about 15 kilometers. There's a broad zone of seismicity, but seems to define, within reason, a broadly planar structure all the way to the surface, so going round about 45 degrees. And then what you see in the leveling line is that the bulk of the movement on the fault to generate those scarps is the hanging wall dropping down. That only a small proportion of that displacement, maybe 10%, is the footwall going up. Now, that's one of the problems we have in geology, is you look at a fault and you see displacement, and the classic thing is we're there a million years later after a fault moved, and you think, well, what moved? Did the hanging wall move or the footwall move? Well, the answer is both of them, but by and large, the bulk of the movement is hanging wall subsidence, and a small component is footwall uplift. But that's the story from earthquakes, is that both move, and you get a small amount of the footwall uplift. Now that becomes important, because if you look at the middle one here, you can see the broad topography of that area is you've got a mountain hinterland in the footwall, and you've got a big basin in the hanging wall. So clearly those kind of displacements that happen in earthquakes get prolonged to actually end up throwing up a mountain on one side and pushing down a rift basin on the other. So modelling work that's been done suggests that in a normal fault, typical normal fault going at 45 degrees through a 15-kilometre thick crust, then you should get, and these displacements are in meters, so 0.2 of a meter, 0.2 minus 0.2 minus 0.4, that you should get in the dashed one is what happens during the earthquake, so a small amount of footwall uplift and a large amount of hanging wall subsidence. But the interesting thing is this model is that then it lets it run, and you get an isostatic response from the lithosphere that induces what we call post-seismic deformation. In other words, you have the earthquake as the elastic break, and then the whole thing kind of readjusts itself in the days, weeks, years following that. And what that does, interestingly enough, is that's a solid line. It pushes the footwall further up, and it produces the hanging wall further up. So what you essentially get is you get the whole thing just getting pushed up, both hanging wall and footwall. So in that case, your topography in the footwall gets ever bigger, but your amount of subsidence gets less. And that's why, for example, if you go back to Strava today, that church is no longer in the water. Because, all right, it's been protected, and I'm sure there's been some gravels in there, but that now sits about a full metre or so above sea level. So that is recovered, post-seismic recovery, as a result of that normal faulting earthquake, what, almost 25 years ago? No, more than that. God, 35 years ago. There are some slightly odd places. This is quite interesting. This is, so that mountain there, that's the mountain of the fault, but it's on the other side. All right, so we've gone to the south. if you go out over the other side of the fault, it's dipping away to that north. And I'll show you a map in a minute which makes this look clear. This is actually the Corinth Canal running in front of us. And what we see right in here is an old Roman ramp. So the way the Romans got their boats across that narrow little isthmus was to actually create a road across, a couple of miles long, drag their boats across. But the interesting bit is that on top of that road, there's beach rock. So that's a Roman road that was built to at least start in the sea, but then to emerge, go over land, which has got beach rock on it. So that tells you that Roman road was formed at or above sea level, to make sense of what its function was. Then must have gone down below sea level to accumulate beach material on it, and then has risen back up again to now be in the present day situation. So those kind of bouncing kind of vertical movement suggests a sort of slightly odd activity here. So that's what the ramp looks like. As I say, an alternative to the modern canal that goes through there, the Roman version of it. But if we look at where it is, it's located, you can see where the canal is. It's located at the northwest end of the canal. And you can see that then lies in the distant footwall of the Pisa Fault. So it's hard to tell that distant footwall, it should be going up on the footwall of the Pisa Fault, but it's quite far away, so it's not going up dramatically. But you'll also see that there's another fault to the south, placed by a place called Keskria. And that is a normal fault. And in that one, the Roman ramp is in the hanging wall of that other fault. So one of the things that you can be getting is some locations can be between the two. So it shows where the Corinth Canal is. This is the Pisa fault that we're looking at in the foreground, and you can see the escarpment for the Kekria fault in the north. And you can see that the Corinth Canal is located about halfway in between. And this is in James Jackson's paper, really looking at the Corinth Canal and showing how a site in here would be in the footwall of this fault, so it should rise up. But every time this one moves, it would go down. So what it's suggesting is this kind of yo-yo type effect in places that are midway distant from some of the faults. So it really depends. What your uplift history depends on is where you are in relation to the fault. So I've mentioned about the fault. The fault is a bigger structure. In fact, you've done a practical on the Gulf of Corinth already. We've been in this area here, looking at the Pisa faults. This is where the canal is. This is the Kekria fault coming through here. But you'll see that actually this Pisa fault is part of a system of a long fault system that runs the length really of the Gulf of Corinth. In fact, it bounds the southern side of the Gulf of Corinth. So although that ruptured in one earthquake here, these are all other sections that could also rupture in earthquakes. And their activity is responsible for the uplift of the Peloponnese. And anyone knows this area, this is very mountainous. This is the kind of footwall block of that big fault that runs along the Gulf of Corinth. So that Pisa one that we looked at, part of a bigger structure. And then in fact, if we then zoom out even more, here's Perahora, here's the Corinth Canal. That's the bit we were looking at. Kekria faults in here, Pisa faults here. These are the ones running along. Well, that's part of a whole system of faults that occur across this whole region. There's another rift system up here, the Evia system. There's another set of rifts that come through here into the Peloponnese. And so together, as indicated on the top right diagram, what it's allowing, there's a whole set of network of normal faults that is allowing Greece to stretch itself. So that earthquake in 1981 was a snapshot of a process that's at the moment tearing Greece apart by extensional tectonics. And all of those faults in there will be operating in a similar way. So that you get a sense of this. This is a DEM. Here we've got, right in the middle, we're looking at the Perahora Peninsula and the Gulf of Corinth. We're looking straight up at it. But you can see that linear mountain range and then Rift Valley, mountain range, Rift Valley, just repeated all the way across that whole landscape. So this is like a classic laboratory for normal faulting.